Hello and welcome to this clip on amines and amino acids. We'll look at the naming and classification of amines and their derivatives amides and also amino acids. The physical properties connected to the presence of the NH2, NHR or NR2 group. The basic nature of amines due to the availability of a lone pair on the nitrogen atom in each case. A synthesis of amines from a nucleophilic substitution of ammonia for halogen on an haloalkane molecule, and some examples of amino acids and how they react with bases as well as acids. As you can probably guess, they contain a basic part, being the amino bit, and an acidic part, hence the acid in the name. Before we go any further, it's worth pointing out that there's a few assumptions in terms of your knowledge and your understanding that are being made during the course of this clip. Acids and bases, obviously, from your first year of A-level chemistry, as well as hydrogen bonding. And also an understanding of nucleophilic substitution is needed for this video to make sense. So if you're unsure about any of those, it might be worth going back and having a look at them before you proceed any further. So the main thing about amines, they contain the NH2 group, and NH2 contains a nitrogen atom, and that nitrogen atom has a lone pair. So if the hydrogens in the NH2 group are slowly replaced by R groups meaning basically organic chains of some kind or organic structures of some kind, then you get a primary, a secondary or a tertiary amine. And it's very similar to the classification of alcohols. So if you've done alcohols already in your first year, you'll know about how to classify alcohols, so it's exactly the same idea going on here. So amines have the same molecular shape as ammonia, at least around the nitrogen atom. But in the case of methylamine, you also have a CH3 group, and the CH3 group will be tetrahedral. So it's important to remember this. This is the kind of thing that's liable to come into an A2 style question, just to test out your knowledge of shapes from your first year of chemistry. So not surprisingly, the first part of the name comes from the R group. What we mean by that is the main organic body of the molecule, and the second part must end in amine. So if we were to highlight each of these structures, the methyl bit, ethyl bit, and the phenyl bit. In each case, the amine part itself obviously comes from the NH2. And as we go from primary to secondary to tertiary to quaternary amines, successive hydrogen atoms bonded to the nitrogen atom are replaced. So as well as the examples we've just looked at, we also have more complicated examples, some of which you may have heard of, such as amphetamine, phenylephrine, or adrenaline. And these three amines in this particular screen, all of them have distinct biological activity. Adrenaline and amphetamine you've probably heard of. Phenylephrine is what's put in an EpiPen. So it's interesting to note that amines, many of them do have a distinct biological or pharmacological activity. So as you'd expect, having a nitrogen atom bonded to a hydrogen atom, they undergo hydrogen bonding. So they not only hydrogen bond to each other, making their melting points and boiling points higher than normal, but also the hydrogen bonds as a result require more energy, which would explain the increased melting point. They're also very soluble in water because of the same reason. They hydrogen bond with the water molecules around them. So they're soluble in water, and in addition they hydrogen bond with each other, so have increased boiling points. So the presence of the lone pair in methylamine, or any amine for that example, basically means that it can behave as a base. So, what does that mean in chemical terms? It means it accepts a proton. So what will be happening is you have a dative covalent bond forming, like so. So for this bond to form, the proton has to be accepted by methylamine, and the lone pair on the nitrogen has to turn into a bonding pair, which then becomes the dative covalent bond we've just talked about. So in phenylamine, this structure here, the lone pair on the nitrogen atom is delocalized into the pi system of the benzene ring in the same way that the lone pair on the oxygen in an OH group as part of a phenol functional group is also delocalized into the pi system of the benzene ring. So that makes the lone pair less available. If the lone pair is less available, the molecule is less basic, but it's less able to bond with a proton. And with aliphatic amines, you have alkyl groups which tend to donate electron density. What that means is the nitrogen atom finds it easier to donate its lone pair and behave as a base. So aromatic amines tend to be less basic, aliphatic amines tend to be more basic. So if we work our way through this screen, which shows us how aliphatic amines are made, it takes place via a nucleophilic substitution mechanism, as you can see. This time it's an ammonia is the nucleophile, because the nitrogen on ammonia has a lone pair. So the product is called a quaternary ammonium salt, in this case propyl ammonium chloride. And the bond between the positively charged nitrogen and the negatively charged chloride ion is actually ionic, so there's an ionic element to this compound as well as the covalent bonds on the propyl group and the NH3. However, it's not an amine, it's a quaternary ammonium salt. So we have to take our propyl ammonium chloride and we have to react it with NaOH. And what that does is create our amine. So our final product that we actually want is CH3CH2 CH2 NH2. But there's a slight problem with that compound in that it's actually a nucleophile itself. If you look closely, the nitrogen atom still has a lone pair. So basically what's got to happen is that lone pair on that nitrogen has got to be prevented from going back and attacking our original chloropropane. So the chloropropane molecule has been highlighted. Obviously there will be chloropropane molecules that haven't reacted yet. So once the propylamine has been formed, there's a danger that it will go back, and instead of the ammonia, it will go and react with the chloropropane. And that'll produce a secondary amine which can then go on and re-react, because the nitrogen will still have a lone pair, with a new molecule of chloropropane to make a tertiary amine. To prevent this happening, we use excess ammonia. So the system is flooded with ammonia. So ammonia is the main nucleophile that's available. To prevent water acting as a nucleophile, because don't forget the oxygen in water has two lone pairs, we dissolve the haloalkane in ethanol instead. So if we take our chloropropane molecule, but imagine that we've now already made some propylamine. The propylamine itself can go back and react with chloropropane. So this is called dipropylamine. And this still has a lone pair on the nitrogen, which can go on to substitute again. So essentially what's happening, you probably see it coming, is you'll have a multiple substitution of propyl groups coming off the same nitrogen. So if left unchecked, the process can just repeat and repeat and repeat until the lone pair on the nitrogen eventually ends up getting involved in a dative covalent bond with the fourth propyl group, and this makes a tetrapropyl ammonium ion, which is drawn slightly badly down the bottom right hand corner of the screen. What this now does is it reacts with one of the chloride ions, because every time the substitution takes place a chloride ion comes off, doesn't it? So this now forms a quaternary ammonium salt called tetrapropyl ammonium chloride. To prevent this problem in the first place, this is why excess ammonia is used at the beginning. Because if excess ammonia is used, then it'll just be ammonia that keeps going back and producing propylamine, which is what we want. Not dipropylamine, not tripropylamine, and not tetrapropyl ammonium chloride. So for making aromatic amines, this time the NH2 group is substituted directly onto the benzene ring. We use a different set of reaction conditions. We need concentrated hydrochloric acid and tin as our reducing agent, because the addition of hydrogen is obviously the same as reduction, just like the addition of oxygen is the same as oxidation. We've got to be a little bit careful in that if we're going to be adding hydrogen, we make sure we're adding the right amount, because if you look at the number of hydrogens that you actually need, you need 6. If you're doing this one, do watch out for balancing. Now the H in square brackets means hydrogen atoms that come from a reducing agent, in the same way that O in square brackets means oxygen atoms come from an oxidizing agent. So we use H to signify the use of a reducing agent. That reducing agent in this particular case is tin and concentrated hydrochloric acid. So an amide can be made by reacting an acyl chloride with an amine. You can also do it using ammonia. In each case, the amide group has been highlighted in grey. And it might be worth making a note of the fact that 2 moles of ammonia or amine are required to make an alkyl ammonium chloride or ammonium chloride, depending on which base you choose to use. So I've labelled the 2 amide products, and I've also labelled the additional side product, the alkyl ammonium chloride in the case of an amine, or the ammonium chloride in the case of ammonia. So let's now have a look at how we might name amides. I'll show you a couple of examples. So the naming of amides is not that different to the naming of amines. So the first part of the name includes the alkyl chain. So in this case we've got propan and 2-bromobutane. The second part is the amide bit. These 2 possible examples are primary amides, because there are 2 H's still attached to the nitrogen. So secondary and tertiary amides are known as N-substituted amides because an additional R group, such as the ones that I've highlighted, are substituted directly onto the nitrogen atom, remembering that the nitrogen atom is there. So in terms of their classification, N-ethyl butanamide would be a secondary amide, N-dimethyl propanamide would be a tertiary amide. It's interesting as well to note in the name for the tertiary amide that the N twice, because it's been substituted twice, or substituted onto twice. And a little diagrammatic summary of the idea of primary, secondary and tertiary amides can be seen at the bottom left hand corner of the screen. So you might be thinking, surely the same idea can be applied to amines. Well, it can. This one would be something called methyl-ethylamine. So the ethylamine will be the main part of the molecule, and the methyl group would be the substituent, because it's smaller, it's shorter chain. In the other example you've put there, dimethylamine, the methyl groups are of equal size, so the di prefix reflects this. So in this question, it shows us an amine, a diaminobenzene, so it's two amine groups on one benzene ring. It asks you for 2 marks to explain what is meant by the term 1,4-diamino. So the diamino means 2 amine groups, not just one, and 1 and 4 is their positioning on the benzene ring. So let's bring the page down a little bit. It says 1,4-diaminobenzene can be manufactured from 1,4-dinitrobenzene. And like you've looked at before, this is a reduction. And as you probably recall from earlier in the clip, the reagents were tin and concentrated HCl, and it was a reflux conditions. So moving the question down a bit, it says complete and balance the equation below for this reaction. First thing to do is to remember that we're actually producing H2O as well as a side product. But the number of H2Os will depend on the number of oxygens you're replacing. If you look at this closely, you can see that you've got 2 nitro groups turning into 2 amine groups. That means 4 oxygen atoms are replaced by 4 hydrogen atoms. So that must mean that you have 4 H2Os. Now what you've got to do is count up the number of hydrogens on the right hand side. You've got 4 lots of H2O, plus you've also got the hydrogens in the amine groups. So in total, from the diaminobenzene, you have 4 hydrogens, and from the water you have 8 hydrogens. So that would mean that you'd need 12 H's in total. So the example we looked at earlier in the clip had 6 H's, but this time we're actually reducing 2 NO2 groups, so it's twice the number of hydrogens. So this part of the question is now asking us about the basic nature, as in the actual basicity of 1,4-diaminobenzene. So you need to say that there's an H plus accepted from HCl by formation of a data covalent bond using the lone pair on the nitrogen atom. There's 2 specific points made there for your 2 marks. Then what they want you to do is draw the structure of the salt formed. Because as we know, amines are bases, and bases and acids react with each other to make salts. So I'm being careful of 2 things here. First of all, that the positive charge goes on to the nitrogen, because that's where the positive charge exists, and also the fact that there's actually 2 amine groups on 1,4-diaminobenzene, so there'll be 2 salts formed, or 2 NH3 plus Cl minuses formed, I should say. And finally, it asks you to say whether you'd expect hexane 1,6-diamine to be a stronger or weaker base than 1,4-diaminobenzene, and explain your reasoning. So let's bring the screen down a little bit to have a think about that. So the first thing to do is make a statement about the fact that the alkyl chain is an electron donating group, so therefore it allows the lone pair on the nitrogens to be donated easily. But if we look at 1,4-diaminobenzene, the lone pair on each nitrogen this time is delocalized into the pi ring of the benzene ring, and is therefore less available to form data covalent bonds and therefore behave as a base. So let's have a quick look at the mark scheme. We got the right idea with the 2 amine groups and the positioning of the amine groups on the benzene ring. We said it was a reduction, and we mentioned tin with HCl, and the concentrated acid under reflux was also included. We got the right number of H's because we got the right number of waters. We said that it accepts H plus using the lone pair on nitrogen, and then a data covalent bond is formed. and then we got the correct structure with two sets of NH3Cl. As in both base groups neutralized, both amine groups neutralized. We said that it's a stronger base because electrons move towards the N, so the inductive effect is the same as the alkyl group being an electron donating group. With diaminobenzene, 1,4-diaminobenzene, we said the lone pair from the nitrogen is delocalized into the ring. So therefore the electron pair is more easily donated. We actually said the electron pair in diaminobenzene is less easily donated, or reverse argument allows you to say either of those two things, so long as the comparison is correct. Okay, so let's move on now to amino acids. So an amino acid is a structure that has a basic and an acidic group on the same molecule. So you have an alkyl chain of some kind in the middle, a carboxylic acid group, and an amine group. And if the central carbon has one hydrogen atom and one R group bonded to it, it's then known as an alpha amino acid. So in this case it's the central carbon that has the R and the H bonded. If there happen to be more carbons between this carbon here and the nitrogen, then you may have beta and gamma carbons as well. But in this particular model it's called an alpha amino acid. So it's worth taking a moment to have a look at the idea of chirality in alpha amino acids. So you may recall that chirality refers to any carbon atom with 4 different groups attached to it. It's called a chiral carbon then. So therefore there's 2 versions of this particular molecule. They can rotate plane polarized light in opposite directions to each other, and for that reason are called optical isomers or enantiomers. So you can apply this idea to your model of an alpha amino acid. So looking at the 2 enantiomers, you can see that they're mirror images of each other, and therefore they'll rotate plane polarized light in opposite directions to one another. So alpha amino acids, you remember, have to have the hydrogen and an R group attached to the central alpha carbon. So in this way the central alpha carbon, which is this part here, becomes the chiral centre. So it's worth bearing this in mind when asked exam questions about chirality. In fact, chiral molecules tend to be very biologically active. Many enzymes, many proteins, many amino acids, many hormones, etc. happen to have chiral carbons in them. And it's important to remember that it's usually only one of the 2 isomers that actually has the pharmacological effect. The other isomer can either be non-pharmacologically active or, even worse, have dangerous side effects. But this is covered in a separate video clip. Not surprisingly, amino acids can react with each other because each molecule has a basic and an acidic end to it. So the opposite ends, so to speak, can react with each other. When they do so, water is released. So in the same way that an acid and a base react to make a salt plus water, 2 amino acids can react to make what's called a dipeptide and water. The peptide linkage is the same as the amide linkage, or very similar to it at least. If you've done some work on polymers, you'll have come across this already. If you haven't come across it already, then when we do polymerization in class, you'll see that as well, a similar reaction. And all that condensation means is the reaction of 2 molecules together to make a larger molecule, in this case the dipeptide, with the elimination of a small molecule, in this case water. So I'm going to set you a little challenge now. I'd like you to work backwards from this section of protein, basically when you get lots and lots of peptide links in a row, you end up with a polypeptide, and polypeptides can hydrogen bond with each other. The chains can hydrogen bond to make proteins. So this is a section of protein, and I'd like you to work out what the original amino acids might be. So grab a pen and pause the video and see if you can have a go. And play the video again when you think you have the answer. So hopefully you were able to suss out that all you really had to do was add water at each of these points here, because that's the reverse of the reaction that we've just talked about. So here we've got some examples of actual amino acids, alanine, glutamic acid and serine. These are examples that might be used and given to you in exam questions. They wouldn't expect you to memorize these structures, but they might provide you with them and expect you to work out what they're likely to do. So what I've done here is I've rejoined them in the same way that I'd taken apart a section of polypeptide in the last slide. And I just wanted to draw your attention to one of the additional COOH groups, the one that you get in glutamic acid. That can actually undergo further polymerization. So you could actually get a reaction between that and the NH2 of another another amino acid molecule. So I haven't seen it in an exam question very often, but it's something that might sneak in just to test out whether you're aware that there's a second COOH group. And by the same token, the hydroxyl group in serine could also undergo things like esterification reactions with other carboxylic acids. So it's just because they're not part of the main amino acid structure doesn't mean that they're not functional groups, just like they'd be functional groups if they were anywhere else in any other molecule. So the message here would be to watch out for other functional groups that can also be found on amino acids. So let's have a look at a typical exam question. It gives you glutamic acid and glycine are both alpha amino acids that occur widely in living organisms. Their structures are shown below. So let's have a look at why they're alpha amino acids. Well, you've got your central carbon, that's your alpha carbon, and you've got the carboxylic acid group in each case, and the NH2, the hydrogen coming off the central carbon. So you may have noticed there's not an R group as such on the alpha carbon in glycine, but it's still considered an alpha amino acid because the central carbon is an alpha carbon. So the general formula they're looking for is like this. I would recommend the easiest way to answer is to just draw the general formula that way rather than try and put it into words. And it says explain how glutamic acid and glycine both fit the general formula. So even though we said earlier that technically H is not an R group, in the exception of glycine, the second hydrogen takes the role of an R group. That allows us to justify glycine being called an alpha amino acid. It's one exception to the rule where we use R to represent the rest of an organic molecule. So generally R groups tend to have carbon chains or rings or such like. In this case, the second carbon is R. So in other words, that's what I'm trying to say. So in this case only, so just to clarify, R is CH2, CH2, COOH in glutamic acid. So let's bring the page down, and it says amino acids react with both acids and alkalis. It asks you to predict what would happen if glutamic acid reacted with excess HCl on the one hand or excess NaOH on the other. They've put the boxes on the side of the molecule that would actually react, so the H2N would react with excess HCl, and the COOH would react with excess NaOH. It's worth pointing out that it's not just the COOH, but also the second one, that's further down the molecule. We said earlier, didn't we, that if you had extra COOHs or NH2s, they would also get involved in equivalent acid-base reactions. So in your first structure, you need to make sure the NH2 group becomes NH3+, and both COOH groups are unreacted. You can add in the chloride ion if you wish, but it's not essential because it's only asking how the glutamic acid molecule itself is changed. And in the second structure, this time both COOH groups become COO-, but NH2 remains unreacted. So checking the mark scheme, it covers what we've just said pretty much. We talked about the structure, or in words. It's interesting to note you can't just say that they both have NH2 and COOH. What that means is that their arrangement required as well. And we made reference to H in glycine and CH2CH2COOH in glutamic acid. The structures we decided are correct, because we got that, and also the fact that COOH are unaffected. And on the next one, we got a mark for each of the COOs being changed into COOH is being changed into COO, and H2 and the rest of the molecule. So hopefully you found this a fairly useful roundup of amines, amides and amino acids. If you have any further queries, obviously bring them into class with you, and maybe have a chat with your teacher or come and see one of us in subject extension. But for the time being, thanks for your time, and I'll see you soon.